Welcome to today's video on the cosmic microwave background, dark matter, and dark energy. Right now, there is an ancient glow that is passing through your room. It's the universe's baby picture, still arriving after 13.8 billion years. We call it the microwave, the cosmic microwave background, or CMB for short. It's a faint, nearly uniform light with a temperature of about 2.725 Kelvin today. Kelvin is a temperature scale that starts at absolute zero, the lowest possible temperature where random microscopic motion is as low as nature allows. At 2.725 Kelvin, this light is extremely cold and gentle. Its strongest glow has millimeter-long wavelengths your eyes can't see. Because space keeps expanding, this background keeps cooling. As distances stretch, the light's wavelength stretches, and its temperature falls in lockstep. If the universe's size grows by about 6% over the next billion years, the background would cool by about 6%. From 2.725 Kelvin to roughly 2.6 Kelvin. Far in the future, as space grows larger and larger, this glow will become even colder and redder, fading deeper into long wavelength radio. Put the cosmic pie together and you get a surprising recipe. Only 5% of what makes up the universe is ordinary matter, the matter that you and me understand. Nearly 27% is dark matter, and nearly 68% is dark energy. That means everything we understand well, atoms, chemistry, you and me, genetics, whatever, is only one part in 20 of the total cosmic budget. The ramifications are scientific and personal. Scientifically, it reminds us to be humble and to test ideas from many angles. Personally, it's awe-inspiring that complex life arose from the 5% we do understand. Even though 95% of the universe is mysterious in essence, its effects are measured precisely and consistently across different kinds of data, which is why scientists treat the overall picture with confidence while still chasing the what is it details. Now, to the big mystery of dark matter and dark energy, two ideas with strong evidence but unknown what it is nature. Dark matter is dark because it doesn't shine, absorb, or reflect ordinary light, but it does pull with gravity and makes up most of the matter in the universe. We infer dark matter from several independent clues that fit together. Stars orbit too fast in galaxy outskirts. Galaxies bend background light more than visible matter can. And the CMB's ripple pattern needs extra invisible mass. It's not ordinary stuff hiding as dim rocks or gas. The early universe element amounts, and the CMB show ordinary atomic matter is only a small share. Dark matter seems to be cold, moves slowly compared with light, and clumps under gravity, forming giant invisible scaffolding where gas later cools and makes stars and galaxies. Why it matters? Without dark matter's extra gravity, structure would grow too slowly, fewer galaxies, fewer stars, fewer chances for planets and life. So we need dark matter for our theoretical models to match our observations. Dark energy is different. It's not more matter at all. It behaves like a smooth energy inherent to space, that makes up the cosmic expansion and speeds it up. We infer dark energy because very long exploding stars look further than they would in a slowing universe. And because CMB data puts galaxy maps plus galaxy maps require a component that doesn't clump yet dominates the expansion today. Where dark matter gathers and helps build structure, dark energy stays uniform and pushes the large scale expansion to accelerate. A simple possibility is that dark energy is a constant energy of empty space. But it might also be a slowly changing field. This is an open, active area of research. To talk clearly about scales, this vast, we need a shared language. That's where scientific notation and orders of magnitudes are so essential to our understanding. Scientific notation writes huge and tiny numbers as a simple number times a power of 10. So 2.725 Kelvin, that's easy. But 0.001 meters becomes 1 times 10 to the minus 3 meters, which is a millimeter. And 13.8 billion years becomes 1.38 times 10 to the 10 years. This lets us compare things separated by ocean size. The CMB's milliliter waves are about the millimeter wavelength versus visible light, it's about the nanometer wavelength. But really, these millimeter wave is about 1 times 10 to the minus 3. And visible light wave is around 5 times 10 to the minus 7. So there's 4 orders of magnitude, a factor of 10,000 between visible light and millimeter wavelength light. It also keeps reasoning honest and quick. Room temperature is about 3 times 10 to the 2 Kelvin. The CMB is about 3 Kelvin, 2 orders of magnitude cooler. Distances step cleanly across the cosmic ladder. 1 light year is about 9.46 times 10 to the 15 meters. The Milky Way is about 10 times 5 light years across. And the observable universe is about 4 times 10 to the 10 light years in radius. Thinking in orders of magnitude helps you ask the right questions. Is this effect 10 times, 1,000 times, or a million times bigger than that one? And which terms can we safely ignore? Loop back to confidence and method for a moment. We don't just have one clue, we have many. And they interlock. The CMB's temperature and ripples, supernova distances, galaxy lensing, and element abundances all tell the same story. Each new measurement adds a piece to the puzzle, tightening the numbers while the broad picture, hot early state, cooling with expansion, structure growth, and late time acceleration, continues to hold. For take-home habits that apply beyond cosmology, use clear units, lean on orders of magnitude, and trust conclusions when most independent lines of evidence agree. And for a human connection to all of this, the warmth you feel from a kitchen stove and the faint glow that fills the sky are chapters of the same story. Energy changing form in a universe that is still unfolding and dynamic. Quick recap. Ancient light fills the sky as cosmic microwave background, a 2.725 Kelvin afterglow, whose tiny ripples, about 1 in 100,000, seeded structure, the structure of stars and galaxies. As space expands, the background keeps cooling and reddening. Today, microwaves, far in the future, even longer wavelength radio. Dark matter is invisible stuff that doesn't emit light, but adds gravity. It clumps, forming the scaffolding where galaxies grow. Dark energy is a smooth energy of empty space that speeds up expansion. It doesn't clump, it pushes the universe to accelerate. The cosmic budget is about 5% ordinary matter, 27% dark matter, and 68% dark energy. We understand the 5% well, the other 95% we infer from its measured effects. Why trust any of this if we don't know what dark matter and dark energy really is? Because independent evidence all agrees CMB ripples, galaxy motions and lensing, supernova distances, and light element abundances tell the same story. Scientific notation helps keep vast scales honest and comparable, right? The CMB waves are about 10 to the minus 3 meters, while the visible light is about 5 times 10 to the minus 7. And there's about 10,000 difference, 10,000-fold difference. Connecting this to everyday life, thermal cameras and microwave ovens use the same physics of radiation. The sky's afterglow is a result of CMB, is simply physics written on the largest canvas of all, our universe. Thank you, and see you all in the next video.